So here's a little rundown on our 3.3 material. I want to go through best practices for Lewis structures, generating valid Lewis structures, what's the best Lewis structure, talk about electronegativity, and partial charges ultimately. Okay, so whenever you're thinking about drawing a Lewis structure, there are a couple of practices. So first and foremost, you have to have certain atoms meet the octet, so they have 8 electrons around them. C, N, O, F are all good examples of atoms that have to have 8 electrons around them. H, however, does not have to have 8 electrons around it. Then maybe one of the most important things about it when you're drawing a Lewis structure is the number of valence electrons. Valence electrons drawn is equal to the number of valence electrons you could draw, or you can draw. So if a structure if you draw a structure with 24 electrons, but all of the atoms combined only come up with 16 electrons, that structure is obviously going to read wrong. When you talk about a best structure, one of the things that you're kind of getting towards is you're talking about resonance, or you're getting towards resonance structures. But before you get to that exactly, one of the things that you're talking about is the best structure is going to have the fewest number of the formal charges. And if it has multiple formal charges, they're going to end up equaling 0 or equaling the net charge for that molecule. But your aim whenever you draw a structure is to have as few charged species or few charged atoms as possible. So you want to reduce the number of charges as much as possible, and you want to, if you have them, make sure that they equal 0 or equal what they can possibly for that atom. Likewise, you want to make the most electronegative elements be the ones that have those negative charges. Okay, now electronegativity is something that's a little bit of a discussion, or sorry, what it kind of gets to is what does an atom actually want within a bond? So if we take something like fluorine, which is arguably the most electronegative element that's regularly found in bonds, between 2 different atoms, like let's say that we have a molecule of HF. Okay, fluorine is very electronegative. So this bond right here, well, that's 2 electrons right there. But that electron density is going to be closer to this fluorine atom than it is to that somewhat positively charged hydrogen atom. Okay, so electronegativity really looks into which atom within a bond wants the electrons more. Okay, so electronegativity helps us kind of explore that and helps for the assigning of charges and whatnot there. Now, when you think about drawing a Lewis structure, and let's say that we drew the Lewis structure, I had a good one that I was going to use as a model. Let's say we had the Lewis structure for NCO minus. Okay, so NCO minus. What this is going to be is, well, how many electrons do we actually have to work with? We've got 5 electrons for nitrogen, 4 for carbon, and 6 for oxygen. I don't know why I wrote 4. Okay, so that's 5 plus 4, that's 9 plus 6, plus our extra electron right here, 1. That's going to be a grand total of 16 electrons that we can draw. Okay, so now whenever we come up with a structure, NCO minus, okay, well, one of the things that we could do is we could go ahead and place electrons around our central atom. There we go. And then around our oxygen. But now, how many electrons are we looking at? 2, 4, 6, 8, 10, 12, 14. we're down to 16 electrons right off the bat, and that nitrogen is nowhere near being a complete octet. So we have to get a little bit more creative whenever we're drawing this. So let's go ahead and put a triple bond between nitrogen and carbon. And then let's put our lone pair to satisfy the octet of nitrogen. Carbon's got a complete octet. Now what else is there? Oxygen. Okay, so let's count our electrons. 2, 4, 6, 8 when we talk about our triple bond. 10, 12, 14, 16. Awesome. So this structure right here shows the correct number of electrons. But we notice that this species right here has a negative charge on it. Now, when you think about the electronegativity of the different atoms here, which one of these atoms is furthest to the right on the periodic table? Well, the furthest to the right on the periodic table, so the most electronegative, is going to be that oxygen right there. And so if you were to assign that negative charge to any one of these atoms, well, it would be that oxygen. So that's one way of looking at it. But we could also look at this as a formal charge calculation. So we can look at how many electrons, our valence electrons minus our assigned electrons. Well, nitrogen has 5 valence electrons, or a core charge of 5, and it has 5 electrons that is assigned. So that's a 0. So there's no formal charge there. Carbon has a core charge of 4, and it has 1, 2, 3, 4 electrons that it is assigned. So 4 minus 4, lo and behold, it's 0. Now, oxygen, on the other hand, we've got a core charge of 6, and it's bringing in, or it sees, it's assigned 1, 2, 3, 4, 5, 6, 7. 7 electrons minus is negative 1. So our negative charge there is on that oxygen right there. So it is the most electronegative element, which is one reason that it's going to, well, have that negative charge, but also it's a formal charge. It's going to give a negative value there. All right, so the last thing that I want to talk about is partial charges. And so, you know, if you're given a molecule like A, X, 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 Y, and you are given specific values for these different atoms, and whenever you're asked to look at what are the possible charges of them, okay, so one of the things that you should think about is where are these different atoms. So think about them in terms of electronegativity. So if this X is something like fluorine, well, chances are that's going to be a negative partial charge on these guys right here. Okay. Now, what we generally need to do is we need to have partial charges that basically cancel one another out. So let's say that this is a negative 2, or 0.2, negative 0.2, negative 0.2. What we have there is ultimately a negative 0.6. If that Y has a positive, or has a 0.3, and that is positive, well, we need to have the A have a positive 0.3 to counterbalance this negative 0.6 that each one of those other atoms has contributed there. So whenever you were thinking about partial charges, basically what we want to do is get those charges to cancel one another out. And think about their magnitude as being, well, equal and opposite. So I hope that was helpful, and I hope this is ultimately productive for y'all for all of your future assessments.